the camera in those rooms also just like face the ground?
So we looked at confidence intervals for beta 1, beta 0. Of course, we would want to make sure that the noise that we have in our data is reasonably low. And sometimes one may say, well, we don't need a confidence interval, just look at the noise and then move on. But there are cases where a confidence interval will be required so people know what amount of variation could we have with certain amount of confidence, just like we do with beta 1, beta 0. Because if I simply gave an estimator for sigma squared, I'm saying, okay, I have a bit of variation. But in theory, if you collect a different sample, that variation could either go up or it could go down for the different sample. So it's always a good idea to have an interval. And notice I don't have sigma, rather I have sigma squared. The reason for that goes back to theoretical statistics. Sigma squared has a known distribution. Coming up with a distribution for sigma hat is a bit more challenging. So I stick to sigma squared. If you find an interval for sigma squared, you can find an interval for sigma. Do you agree? All I have to do is take the square root. We'll do that at the very end. So I've seen degrees of freedom for simple linear regression before. What is it? So n-2, what is the estimator for sigma squared? So we have to make use of the estimator to come up with an interval. That's exactly what we've been doing. With beta 1, we use beta 1 hat. With beta 0, we use beta 0 hat. So n-2 estimator for sigma squared. Which is ms res. And in the denominator, chi squared, I'm going to do 1 minus alpha. But let's look at the table that we have. We may have to change it to alpha. It doesn't matter whether you have 1 minus alpha, alpha, same thing. If you have to take a guess, what degrees of freedom should go here? n-2. We need an upper bound. So that's the lower bound that we have. And 1 minus alpha, what is that notation? Chi squared. So chi squared. Here is a question. Could the chi-squared distribution be negative? Cannot be. The square cannot be negative. And it is right skewed. just like an F distribution. Last time I mentioned you've got the right skew distribution, divide by a right skew distribution, you end up getting a right skew distribution, which was F. F comes from chi-squared divided by chi-squared. Okay, so I am going to an area of alpha. And what is that number over there? What is it called? Starts with the letter C. Critical value. Good. Now, I picked one using alpha. Yes. Next. I picked one, and exactly what you say. I picked one value, which is chi-squared 1 minus alpha, comma, n minus 2. Now, that could only give me a one-sided interval. Do you agree? Because I have one number here, and then all the way up to infinity. That is okay, but I would rather have a lower endpoint and an upper endpoint, rather than simply saying, well, I'll start here, go all the way up to infinity. So we've got to do something. And what is 1 minus alpha over 2? 1 minus 0.05 divided by 2. I will get 0.975. Okay. So if I use alpha divided by 2, I would end up getting 0.05 divided by 2, which is 0.02. Good. So I will have alpha over 2 and 1 minus alpha over 2, which would be 0.975. This critical value over here is correspond to which of the two? Is it 1 minus alpha over 2, or is it alpha over 2? This number right here. Once we divide and have alpha over 2, 0.975, should it be here or there? I'll give you a hint. This is 0.975 because the area below is 0.975. Yes, bigger area. The lesser one would be right here. So chi-squared alpha over 2 comma n minus 2. Over there, chi-squared 1 minus alpha over 2. Good. So the upper endpoint is the bigger number. The lower endpoint is the smaller number. That said, what should go here? Should it be chi-squared alpha over 2 comma n minus 2? Or chi-squared 1 minus alpha over 2 comma n minus 2? You tell me. Algebra. That said, clearly that number is small and that one is large. What should go in the denominator? Should it be that number or that number? So, should be the second. Why?
Is that what gives you a larger denominator, which would make that value smaller?
That would give me a larger denominator, which would make the entire number smaller. The lower end point has to be less than the upper end point. So this is 1 minus 2. And on the other side, I will divide it by the smaller denominator, which would make the end results here large. Now, worst case scenario, if you forget that you can come up with the interval and then you realize the upper end point to be less than the lower end point, you just flip it in. Does that make sense? Worst case scenario. Are we clear? And that is how we find the confidence interval for sigma squared. The estimator, we should always use the estimator in finding a confidence interval, and that here is sigma hat squared. Good. Perfect. We have a model for this. The fitted model is y hat 41.2 plus 11 times x. That is our model. We did another, we did significance testing. We had a reasonable model. We have a reasonable fit. We found MS spreads. MS spreads, MSE, one and the same. Some books would call it as MSE. I believe your book calls it as MS spreads. We found that value. What is that value? So 9.6 would go over there. We are going to use an alpha pointed I so it relates to that. Cannot trace. N 5 is a 5. Good. Okay. So our data have 5 observations, so 5 minus 2, 3 times 9.6 divided by chi squared 0.975 3 times 9.6 divided by chi squared 0.85. Where do we find the denominators from? So what we have here is a chi-square distribution. Of course, you know, just like the F distribution, the notation is slightly different, but that's okay. All you have to understand is the green area up there is the shaded area here, and the area over here would be the other side, but alpha over 2. So all you have to know is understand what the area below is. The table is going to give you values for chi-squared above a certain value. When in doubt, you can always go up there and look at what they have specified. They are giving you chi-squared bigger than a certain number. So, upper tail, what do we have as the area in the upper tail or right tail? So we have 0.025. So in the table, should we, or from the table, should we pick the column corresponding to 0.025 or 0.975? 0.975.
You're gonna do both either way.
Huh?
You're gonna do both either
We're
way.
gonna do, I was about to mention that, we are going to do both either way, and if you mess up, you could always switch the interval around, yes? But I want you to think, don't think like that. I want you to think. So, would you pick 0.025 or 0.975? Why 0.975, Joe?
I don't have to do the subtraction.
Huh?
I don't have to do the subtraction.
You don't have to do any subtraction, okay? But the table is giving you values for the area above. So what is the area above here? The green area in the table would equal to 0.025. So which one would you pick?
0.025.
0.025. The degrees of freedom is 3. So I would have 9.348. Not next to this. 9.348. Lower end point. In my notation, I have x squared, excuse me, chi squared 0.975, 3. But that table is looking at the area above. Either way, I'm looking for that critical value. What is the area below the critical value?
0.025.
0.025. If that's the case, what is the area above? Can't hear you.
0.975.
0.975. So from the table, what value would you pick?
0.216.
What?
0.216.
0.216. Okay. Oh. And what do we get? Huh? They are backwards. I wonder why. I wrote it as the opposite. It has to be, this has to be 1 minus alpha over 2, and that has to be alpha over 2. Because the area below, as I said, if you mess up, you can always fix it at the end. So I did.
I thought you said not to do that because it was thinking like me.
I see a lot of things. Don't take them seriously. Do take this seriously. Okay, so we just do flip. So that would be 9.348. So Joe, actually right. And this is 0.216. That is 0.025. Right. Makes sense. Because you have more area here, that would be a bigger number. So the table is doing it in reverse. So based on the table, what is alpha over 2? 0.025. And that is 9.348. And that is giving me the upper tail, which just stick with the table. Bigger number. Okay. I'm going to stick with that's the table's notation directly. So we'll just go with what the table has. So that is correct. What do we get?
3.081 and then 133.333.
Now, mind you, that is the variance, not the standard deviation. Shouldn't get it's big. Say, oh, that's a huge number. That's the variance. What matters to us is the standard deviation. If you take the square root on both sides, what will we get?
Lower bound is 1.755.
I'll put it as 1.76.
Upper bound is 11.55.
11.55. So I mentioned the interpretation of the table is critical. So you have to be careful, just like how we kind of went back and forth. In this problem, even if you mess up, same with the table, even if you mess up, you can flip things around at the very last step. The lower endpoint has to be less than the upper endpoint. What is the difference between a t-distribution, the interval that we found for beta 1 and beta 0, used critical values from the t-distribution? There, it was a bit easy. What is there?
You just had to look at whether or not 0 is an interval.
Oh, that's for significance. That's not my question. Finding the critical value was a bit easier in that case.
There's an inverse t.
One, there is inverse t. Another, symmetric. The distribution is symmetric, right? You find one side, you get the other side. So it doesn't matter which column you pick here, it matters. Even if you mess up, you switch it around at the very last step. So a bit, there is an extra step when it comes to chi-squared because it's not symmetric, it's right. T on the other hand, you have the calculator. If you're using the table, it doesn't matter which area you pick, they are symmetric. Okay. Should we call that the variance a bit too high? The standard deviation is about 11.55. The variance is 133. Is the variance a bit too high?
Yeah.
Variance corresponds to noise. Lot of noise. Mind you, when we did the ANOVA, when we fitted them on, when we estimated the value, this was 9.6. Yes. And then we took the square root to get the standard deviation. Our conclusion, everything that we obtained is based on that number, correct? Single value. But in statistics, we don't look at a single value because there is variability. The variance has variation. So what we are trying to say is if I kept repeating this particular experiment right there over and over and over again, the variance could fall anywhere between 3 and 133.33. That is a lot of noise. So this time, we got lucky, we're right, maybe around 3 point something. But next time, it could be 17.84. Does that make sense? So at this step, let me ask you a question. Is our tiny experiment here with 5 observations reliable? Hannah? Oh, I can't hear you.
I don't think so.
Hannah doesn't think so. Why?
Because your population size is too small.
Population size or sample size? Sample size is too small. Also, this variability is too high. I can't take the risk of, for example, someone else sampling and getting a variance of 72.84, right? So ideally, if this number ended up being, say, 1.2 to 2.4, that is reliable. Because you're saying, even if you repeat this experiment over and over again, the variability will be between 1.2 and 2.4. Reasonable. 0.5 and 1.1, reasonable. But here, not so much. Why does that happen? It's happening because of the sample size. We have a very small sample size. So, what are the key things to note in terms of what we did? Well, we fitted the model. We had a good ask for it. We have a significant beta 1, as beta 1 hat, is significant beta naught, using beta naught hat t-test. But at the end, we see that there is a possibility to have a large amount of variation. So I cannot finalize and say, I'll just stick with this tiny little sample. We need slightly bigger sample. Does that make sense?
Non-parametric inference.
It's not to go there. Now, what if you're not able to get a large sample? Parametric statistics. If you use non-parametric inference, a small sample size is reasonable. 5, in my opinion, still a bit too small, but it is a bit more reliable than this. Non-parametric statistics is used for small sample sizes and for data that doesn't satisfy properties or assumptions that we make about the distribution. Fundamental assumption here, very first day of class, is that the error or the noise is normally distributed. If that is violated, then you can't use it. You have to rely on non-parametric statistics, which is a bit more complicated. Good.